Welcome again. Hello everyone, and let us continue from the last lecture concept which we discussed about this D'Alembert principle of virtual work, and then we discuss about the D'Alembert's principle which was for the dynamic equilibrium. So in the D'Alembert's principle, if you remember, when we applied forces and then we develop a concept of reverse effective force on the basis of the Newton's third law, that Newton's second law, F is equal to dp by dt, the rate of change of linear momentum, and that finally gives this expression which is the D'Alembert principle, which tells me that the sum of all whatever the forces acting on the system, if for that corresponding we have a reverse effective force, and if I sum all these forces, that difference of all those forces, Fia minus Pi dot, so for as a applied force, then the virtual displacement consistent with the constant is take the dot product of with this, all these forces are going to be 0. So virtual work done by this force, difference of force, applied force, and this reverse effective force, and to displace the system through some imaginary virtual displacement is going to be 0. So we have seen that this is important for establishing to determine the condition for the static equilibrium of the system. We have done one simple example for that. Now let us do two small example based on this D'Alembert's principle, because again on the basis of the D'Alembert principle we can calculate what is the condition for which the system is going to be under a static equilibrium, because actually my system is in dynamic equilibrium, and then using that condition of reverse effective force, that when we apply a force there is minus p dot is there, and then my system is now static equilibrium. For example, if I say that use D'Alembert principle to find the condition of a static equilibrium, this is my system of a pendulum. So I have here is force mg is there, and because of, so we are not actually worrying about this constant force, because we know already that constant forces, due to constant forces, the total virtual work done is going to be 0. So what we are going to do, imagine a virtual displacement, that is my delta I, very infinitesimal small amount of increase in the angle. So and there is because of this there is no inertial forces if we are considering, so the mass moves only due to the gravitational force. So what do you mean by there are no inertial forces? That means there are, I'm neglecting the air resistance. So air resistance is there, the initial inertial forces. Because of that uh, uh, this reverse effective force will going to be there. So if I see that because of, if I apply this force F, and then because of this delta theta is going to be this small displacement, virtual displacement is that, and that is related with my delta r here, because whatever I do is displacement, this displacement, that is going to be this delta theta, and this is my delta r is two component, delta x and delta y, as you can see here and here in this case, and that those are consistent with delta x is equal to L cos theta d theta, because delta x, if we say delta x is my, this is my, if this is my L, so this is my theta, or then I can find this is L cos theta and this is L sin theta. Okay, so then I find delta x is cos theta delta theta, because delta x is in this direction. If I have, so this is L is constant, so this sin theta goes to cos theta and this theta goes to delta theta for this imaginary small infinitesimal displacement. Similarly for delta y is L sin theta delta theta. And r, if you remember, r the position of the coordinate, position of this if I depends upon x and y, whatever it is, this is my x and this is my y, so x and y, so this is L sin theta. Okay, this is my L sin theta, this is in this direction, x direction, and this is L cos theta, this is in opposite minus this is basically this is my positive x plus j direction, and because this is, I'm considering this as minus j, so this is minus cos theta j, this is my r. Okay, So D'Alembert's principle gives us that this Fi minus the inertial forces MIAI dot delta Ri is going to be 0. So because there is no inertial forces, so neglecting air resistance, okay, neglecting air resistance. So I just have this Fi, which consists of the two forces. This is one F and then another one is mg. Okay, so this is F plus mg and I have delta Ri. Delta Ri we have calculated with delta, this is delta x plus delta y. So if I put into this is F, so F times L cos theta delta t, and this is m times L sin theta delta theta. Okay, so what else is going to be 0? So this L is cancel out mg. So if we take this side, so F equal to uh, mg, this one mg L sin theta delta theta divided by L, from here L cos theta delta theta. So these two cancel, L is cancel, and sin theta by cos theta is my tan theta, and this mg is there. So now for a static equilibrium, the condition is that the force which are applying this F is have to be mg times tan theta, okay, for this virtual displacement. So now with this, with the condition of the D'Alembert principle that this Fi, the total forces which are acting on the system, minus the inertial forces all together, if I take the work done by that, is going to be always 0. If I put this condition into my mechanical system, you are going to get the condition for the static equilibrium. Let's try to understand again with some other example, that on the basis of the D'Alembert's principle, let's try to find the condition again in this a small example, that this is my pulley, mg is there, and so what we imagine that if I raise this through this force, if one force is acting on the system, so the tension is acting on this force, the tension here, the tension will be here in this rope, that is going to be the constant forces or inertial forces. So if I raise this by delta x, if I raise this by delta x, then because you know in the pulley condition this is going to be delta x by 2. Okay, so in a virtual displacement which is in the end of the string, if I raise this by delta x, then this is raised by delta x by 2. Okay, so this weight is raised by delta x by 2. So there is no inertial forces, we are considering there is no resistance, constant force is only there, that is the tension in the string. And then now we apply again this inertial forces, there is no inertial forces, I am applying the D'Alembert's principle. So this, the force which is acting on this my F, and this another force is my mg. So F plus mg, and this delta x, what is the virtual displacement, is going to be there. So F time delta x, mg times delta x by 2. For mg, this delta x is delta x by 2. So then from here you get the condition that if m is equal to mg, half of the mg gravitational force, then the system is in static equilibrium. Okay. So this is the condition, this is how you find the condition, how you apply D'Alembert's principle to find out the condition for static equilibrium. So what you have to do, you have to figure out these forces, what kind of forces are acting on the system. One is F and one is mg, and then you have to figure out what are the inertial forces acting on the system. Naturally in the pendulum we neglect the air resistance, here also there is no inertial resistance, sort of friction and all this we are neglecting. So then this part is this part is not contributing for us, so the life is simple. In the next example we will consider this inertial forces also, because you see that there is a pulley and we have a mass m1 and m2 here, and this is the gravity is in downward direction, this is this distance is x from here to the distance. So I had to find the acceleration of m. So now let's imagine a virtual displacement which m moves downward. So what I am considering is m is coming downward. Okay, m is coming downward to a distance delta x, to a distance delta x. So you see this is delta x. So what are the forces? One force is my mg. So if I suppose this m1g force is acting on this mass m1, and delta x is displacement. So the work done by the gravitational force is going to be, let's say, wg1. Similarly for this mass m2, so this is going to be this will go upward because this is coming downward, so this will go upward. So I have minus delta x, and m2g is the gravitational force which is acting. The work done by this is going to be wg2. Now the acceleration, so acceleration of m1 is x dot, because if this m is coming downward, so what is this x is there, so x dot is the acceleration of m1 which has to be downward, okay, and that is m2 is upward, okay. So when this is coming down, so acceleration is downward, when this is going up, so m2 the acceleration of m2 is upward. Now the force which is acting, so force is like force which is going to be m1 mass times acceleration for this m1 force, and this is the inertial force on m1 upward, and this is the inertial force on the m2 downward, which this is m2 downward. So you see that the force acceleration, there is a catch here, the acceleration of m1 is downward, acceleration x dot or this is downward, but the force acting this is upward. Okay, so this is F11 upward. Because of that force, because this force is what? This force is the inertial force, okay, which is resisting the motion. So if I applied forces minus mi ai double dot. So this force is going to resist the applied force, okay. So if I coming downward, because of this force is naturally has to against this force in order to make it in equilibrium, static equilibrium. And similarly for if this force is coming this and so this is going to be in upward, so acceleration is upward, so force is going to be downward for this m2. And then so work done by these inertial forces going to be m1 the force, uh, and this delta x change in this. So this is inertial work on m1 because of the work is done by the inertial forces, and this because of the m2 is the inertial work on m2. Now use the D'Alembert's principle, that is this is delta r is going to be 0. So the forces which are acting and the sum of the inertial forces. So this one Fi is my this m1g and m2g, so that is going to be m1g and m2g, and the second force is this inertial forces which is going to be m1 m2 and with the x dot, okay, this is the acceleration and delta x. So if I put equal to 0, what you get is x dot, this condition of x double dot is m1 by m2 plus m1 minus m2 upon m1 plus m2 times g. So the acceleration, if the acceleration is this, then this is the acceleration of what? This is x dot. Okay, this is m1. So what you have to find? Use the D'Alembert principle to find the acceleration of m1. So we figure out the force which is applied force which is acting. What is the inertial force which is acting? If we consider the inertial force, and then using the D'Alembert principle, we consider that what is the acceleration of the m1. Okay. So you see that my D'Alembert principle help us to define, to reduce a dynamical system to the statical system, static equilibrium system, and then sorry, not a statistical, that is static equilibrium system. And then this is very important to determine the Lagrange equation of motion. So we will quickly see that what is Lagrange equation of motion. So before that, if you concentrate on the expression of this D'Alembert principle, so there is no constant force, only the applied force, and then you have the inertial forces. So now our aim is to transform this principle, which involves the virtual displacement of generalized coordinates. Till now we were talking about the coordinates which are dependent in the physical space. Okay, now we try to work out in terms of the generalized coordinate which are independent. But why we know, why we need this? Because we know that the coordinate, for example, these coordinates Ri are connected by constant. So x square, for example, in simple pendulum, x square plus y square equal to L square. So R is connected, okay, through the constant that there is a fixed length of uh, the length of the simple pendulum, that is L. Thus, in general, if the displacement delta Ri are not independent, we cannot equate their coefficient to 0. So, if this is not independent, so this is dependent, so we cannot put this equal to 0, cannot put this equal to 0. But if my this displacement is in terms of the generalized coordinates, and we know that generalized coordinate are independent. So, if generalized coordinate independent, then if this is independence, then whatever the coefficient of this, which is going to be the force, I can put this equal to coefficient equal to 0, and from there we can find the different conditions and different dynamics of the system. This is what we want to, this is what we want to transform my coordinate system from this physical space to my configuration space, where I can work with the independent coordinate, which are the generalized coordinates. Okay. So, now let's come to how we are going to do it is through the Lagrange equation of motion, that is using the D'Alembert's principle. So, what is a Lagrangian for a system? So, for now, we define the Lagrangian of a system is a quantity which is like given by T, this is the kinetic energy of the system, and V is the potential energy of the system. So, if I have a quantity which is giving me the kinetic energy minus the potential energy, that function is going to be the Lagrangian of a system. But T and V are both scalar quantity. So, naturally this L is going to be, this is the Lagrangian, is going to be the scalar function, okay, because these two T and V are both are a scalar function, that's why the L is going to be the scalar function. So, hence the Lagrangian must be invariant with respect to the coordinate transformation. So, because it is a scalar quantity, you go from one space to another space, there must be invariance for this Lagrangian, that is T minus V. So, let us try to go from this physical space from R to my Ri to Qj, okay, that is we define from a physical space to the configuration space, or some dependent to independent coordinate, that is the generalized coordinate. So, we do with this that my Ri is like transformed through the generalized coordinate, that is q1, q2, q3, and then if I try to write the velocity, that is if I differentiate it, that is dr by dt, because r depends upon q, r depends upon q. So, first I will differentiate with respect to q. So, this r, differentiate r respect to q, and because I am differentiating with respect to t, so first what we do is on r which depending upon q, r with respect to q, and then q with respect to t, okay, and then it also depends upon t. So, that is delta r depends upon t, because now we this, if you do delta t by delta t, is going to be 1 anyways, okay. So, this del q by delta t is my q dot here, and this is delta r by delta t, okay. This is one step. Another, so I have delta Ri is say delta Ri by delta Qj, Q dot delta R by delta T. So, now if I take this differentiate this Vi with respect to Q dot J, and Q, this is the partial differentiation, and Q dot is only at this place. So, this is the Q dot is not there. So, if I partially differentiate delta Qi, delta V with respect to Qj, so what is left is here is this quantity, okay, delta Ri upon delta Qj. This is important relation, we are going to use it. So, I am taking it as equation 1, okay. Now, we define the virtual displacement, that is delta Ri. So, because now my Ri depends upon Qj and T. So, this is R with respect to Q, and then Qj, and then r is also depending on t. So in general we define the displacement, not the virtual displacement. If I put t delta t equal to 0 in this case, so now we have from here to this delta ri. Okay. Now we substitute the D'Alembert in the D'Alembert principle. You have D'Alembert principle. You have this is Fi minus p dot and dot delta Ri equal to 0, where this is my virtual displacement and this is my inertial forces, this is applied forces. So this expression I am putting it here in this delta Ri, and now I am going to open it. Okay, I am going to open it for, so what I get here is Fi. Again, I have written this expression. So this is Fi with this delta Ri Qj, and the second is with Pi minus and Pi, and I have delta Ri delta Qj. Okay. So if you remember this quantity we defined as this generalized force. We had already defined this. So this is going to be Qj, because this quantity times delta Qj is here, and then I have this exactly as same here. Overall delta Qj is going to be 0. So D'Alembert principle is there. So this is my, I'm giving this equation G, where this Qj is my components of the generalized forces. Now let us consider the second term. Let us concentrate on this term. What is this is? So this is Pi and delta R by delta Qj delta Qj. I can write Pi because this P is P dot is delta P by delta T, and it is d dt of this is M and R I double dot. Okay, so because this is acceleration, dr by dt, because this is P is going to be, or say this is going to be from here d dt of this is mv. Okay, so this is going to be d dt of m d d2 dr by dt, and then we take m constant, so this going to be d2 dt square by r. So that is going to be this is going to be r double dot. Okay, and this delta r upon delta qj. Now this again I can rewrite this as delta qj we take outside, because this is sum over j is here, because j indices is with the qj, so it's sum over j we take outside, and then this we I will left with I, because sum over ij is there, we are I is here. So I'm writing this this whole, this is as d dt of mi delta ri minus mi delta ri, because this, if I write, if you see this, if I, this is my first function, this is my second function. So if I take the first function d dt of or say this is d dt of mi ri dot and keep constant, this is delta r upon d delta qj. So this is going to be mi double dot, because d dt is there, so I get this thing, and then this is there, and the next term with this is come with plus. If I take this mi r dot constant and then have d dt of delta r upon delta q. So if I minus this from this expression, then I'll get only this thing. Okay, so which is my this equation. Okay, so just an add and subtract concept. So this is going to be equation V. So in the last term here we can interchange. So in the last term we can interchange here the differentiation with respect to t and q. So because this is all in this term, we can different. Yeah, I can write before this, and so d dt of delta r, this is d dt of delta r upon delta qj. So I can write it qj first, and then if I interchange this, I can write qj first and delta t again. So this delta t upon d dt of ri is basically ri dot. Okay, so then if you remember the expression of delta ri upon delta t, this one uh, delta ri upon delta t, this expression, I'm going to use this expression there. I've used this expression there here, itself with this delta delta qj, this delta delta qj here, and then I ri dot की जगह हमने we have used this expression from equation A, and then becomes this delta delta q, delta delta square delta ri q dot, and this delta square delta qj, this is delta qj delta t, and this is going to be, because this is what I am written, delta vi upon delta qj, because this ri dot, dot is nothing but my vi. So this is, in place of this I have written dv on delta qj, and also from equation 1. So this delta vi upon delta qj is also going to be delta ri upon delta qj, if you remember this one. So we have two things. If delta vi upon delta qj dot, we are going to use delta ri upon delta qj, and then this for this I am going to use dv by dj. So in this expression, so this in this expression, equation B, I am going to use at this place and at this place. Okay, so this is my equation, that delta ri upon delta qj. So at this place I am going to use this one, delta v upon delta qj dot, and this is what I am going to use is delta vi upon delta qj, delta vi upon delta qj. Okay, so delta qj is there, and then this quantity is nothing but del delta qj dot of t. This is t is nothing but half mv square, because we already discussed it, that this is, if I have v dot d dq of v, so I can write it d dq of this is half v square, I can write it na, like this. So using this expression I write it, and this is going to be half mv square here, because m with m is there, and this similarly this for this one, this is going to be delta delta q of t, that is half mv square. So this is half mv square. So with all these, the second this was the expression we have started, that is equation E, and in that we have the concept of this generalized coordinate, and we figure out this, the second term, which was coming out to be this d dt of delta qj dot dt and delta qj upon t. So this is what I have is here. So first term and the second term. So overall, if you remember, this is fi minus p dot delta qj. So this gives me this expression, and because of this I get this the whole d dt of delta t by delta qj. Okay. So if we rearrange this, what we get is this equation. Okay. So in the case of holonomic constraint, the generalized coordinate qj's are independent, and we obtained. So now we see that these are independent coordinates, so we can put this coefficient of this equal to 0. So when I put this equal to 0, so this whole thing into bracket is going to be equal to my qj. This is what is the Lagrange equation of, known as the Lagrange equation of motion. But for this holonomic constant, where this generalized coordinate are, so if you remember from where we started from the argument that this this r jo that was earlier fi minus this delta ri, these were all dependent, so we were not able to put this equal to 0. So we transform this ri to my independent generalized coordinates, and then we can equate this equal to coefficient equal to 0, and so this from that condition we get equation that is known as the Lagrange equation of motion. Okay. So I hope this is all for this, because the next we will discuss from here that how can we modify this Lagrange equation of motion to something more important, including the potential concept, because the force is there itself here, and now we will discuss upon this force. that if the forces are constant forces, conservative forces, whatever forces are acting, depending upon that, what is going to be my Lagrange equation of motion. And then in the further lecture we'll discuss what is the importance of Lagrange in dynamics, because now we are building the theme of the course, that we are going to learn how to write the Lagrangian and Hamiltonian of a complicated system with certain constraint. So with this remark, I thank you all for concentrating and try to learn the thing which I'm delivering, and concentrate on the concept and try to learn, because this course is a very important course for from the all perspective, from all perspective competition point of view, as well as the logical thinking and mathematical precision. This course is very important. So I hope best of luck for all of you. Thank you.